This video lecture provides a background on climate as it relates to concepts in ecology and environmental sciences. The primary source for this lecture is Smith & Smith, Elements of Ecology. As you may expect, living organisms require certain physical conditions to survive, which vary from location to location. The term habitability is defined as, quote, the ability of the physical environment to support life, quote, Smith & Smith. Over both short and long time scales, organisms interact with the physical environment. For example, in short time scales, an organism's physiology and resource availability is influenced by the physical environment. However, over long time scales, perhaps over several generations, the physical environment is influential in natural selection. Two important terms to differentiate are weather and climate. We think of weather as the combination of temperature, humidity, precipitation, wind, cloudiness, and other atmospheric conditions occurring at a specific place and time. Weather is in the here and now. Conversely, climate is the long-term average pattern of weather. So while the average of weather equals climate, these two terms are not directly interchangeable. This is an important distinction. The weather patterns on Earth, for example, the distribution of rainfall, are influenced by the solar radiation intercepted by the atmosphere of Earth and by the rotation and movement of the planet. This has a direct influence on the prevailing winds and the ocean currents. By definition, solar radiation is the electromagnetic energy or stream of photons produced by the sun. Electromagnetic energy is measured in terms of wavelength, which is the physical distance between successive wave crests, and frequency, which is the number of crests that pass a given point per second. While all objects emit radiant energy, the energy emitted depends on the temperature of the object it is coming from. The hotter the object is, the more energetic the photons and the shorter the wavelength. Just over half, that is about 51% of the solar radiation that reaches the top of the atmosphere of Earth is actually absorbed by the surface of the planet. The remaining solar radiation is primarily reflected and scattered by the atmosphere and clouds. Earth not only receives solar radiation, but emits its own long-wave radiation. And in sum, the energy emitted by the surface of Earth exceeds the solar radiation absorbed. This is in part because solar radiation is received during the day, but Earth radiates energy both day and night. Also, the atmosphere captures most of the radiation emitted by the Earth, and this energy is radiated back to Earth. This is called the greenhouse effect. As Bidwani notes, quote, of all the sunlight that passes through the atmosphere annually, only 51% is available at the Earth's surface to do work. This energy is used to heat the Earth's surface and lower atmosphere, melt and evaporate water, and run photosynthesis in plants. Of the other 49%, 4% is reflected back to space by the Earth's surface. 26% is scattered or reflected to space by clouds and atmospheric particles, and 19% is absorbed by atmospheric gases, particles, and clouds. End quote. The amount of solar radiation intercepted at any point on the surface of Earth varies by latitude with a gradient of decreasing temperatures from the equator to the poles. At higher latitudes, solar radiation hits the surface of Earth at a steeper angle, so that sunlight is spread over a larger area. This incoming solar radiation must pass through a deeper layer of air, and so it encounters more particles in the atmosphere and is reflected back into space. We also recognize distinct changes in seasons, especially at higher latitudes, as the result of the inclination or the tilt of the Earth of 23.5 degrees, and the movement of the Earth, that is, the Earth maintains a 24-hour rotation and a yearly movement around the Sun. Across most of the Earth, though not at the equator, the diurnal cycle, that is, the hours of daylight and darkness, varies with the season. The equator receives 12 hours of daylight and night throughout the year. Solar radiation falls directly on the equator during the vernal equinox and autumnal equinox, which is depicted in the figure to the left. Solar radiation falls directly on the Tropic of Cancer, which is at 23.5 degrees north latitude during the summer solstice, shown in the top right image. Solar radiation falls directly on the Tropic of Capricorn, which is at 23.5 degrees south latitude during the winter solstice, shown in the lower right image. The seasonality of solar radiation, temperature, and day length increases with latitude. For example, at the Arctic and Antarctic circles, which are at 66.5 degrees north and south latitudes respectively, day length varies from 0 to 24 hours over the course of the year. This variation in exposure of different latitudes to solar radiation controls mean annual temperature around the globe. Air temperature decreases with an increase in elevation or altitude up to 11 kilometers. Likewise, atmospheric pressure, which is the amount of force exerted over a given surface area, decreases with an increase in altitude. The atmospheric pressure at any point is measured in terms of the total mass of air above that point. One important vocabulary term is the environmental lapse rate, which is the rate at which temperature decreases with altitude. As you can see in the figure to the left, the red line shows that air temperature has a complicated vertical profile. Air temperature does not decline continuously with increasing height above the Earth's surface. The British geographer notes that, quote, as you climb a mountain, you can expect the air temperature to decrease by 6.5 degrees Celsius for every 1,000 meters you gain. This is called the environmental lapse rate. For example, if air temperature is 30 C at sea level, as shown to the left in the image to the bottom right, you can expect temperature to have fallen at 10.5 C at the altitude of 3,000 meters. This phenomenon takes place firstly due to the source of heating being at surface level, and secondly because of differences in pressure. Air at higher altitudes is cooler because the pressure is lower. Gases expand at lower pressure. As a gas expands, the molecules and atoms within it move more slowly. Since air temperature is just a measure of how fast the molecules in air are moving, the rate of motion of molecules and the temperature are both lower at higher elevations. Secondly, the troposphere is warmest at sea level and cools upwards because the Earth's atmosphere is heated from below. The atmosphere is mostly heated by the surface of the Earth below and not directly by the sun from above, even though the upper atmosphere is closer to the sun. Therefore, the higher you rise in altitude, the less surface area there is to heat the air around it. The resulting environment is one of greater extremity proportionally to altitude. This means colder and more extreme atmospheric conditions combined with steep and weathered surfaces. End quote. From the British geographer. In the last slide, as here, you can see that the layers of the atmosphere above the surface of Earth have distinct names, though the height of the boundaries are somewhat variable. Starting closest to the surface of Earth is the troposphere, which is the layer in which all weather occurs. The boundary between the stratosphere and troposphere is called the tropopause. The second layer up from the surface of Earth, the stratosphere, contains the ozone layer. The stratosphere is the layer where volcanic gases can affect the climate. The boundary between the mesosphere and the stratosphere is called the stratopause. The third layer from the surface of Earth is called the mesosphere, which is the layer in which most meteors burn up after entering the atmosphere of Earth and before reaching the surface. The boundary between the mesosphere and the thermosphere is called the mesopause. It is the coldest place on Earth. In the fourth layer from the surface of Earth, which is the thermosphere, temperature increases with height. The temperatures can rise to 1500 degrees Celsius, but it would not feel warm because of the low air pressure in this layer. The exobase is the lower boundary of the exosphere. This outer atmospheric layer, the exosphere, contains few particles that move into and from space. The International Space Station orbits Earth in this layer. The atmosphere of Earth is in a constant state of movement that is driven by rising and sinking air masses and by the rotation of Earth on its axis. Air heated in the equatorial regions rises to the top of the troposphere, and as this air rises away from the Earth, an area of low pressure establishes at the surface. Most air rises beneath and causes more air rises beneath and causes the air in the troposphere to spread towards the north and south poles. Air that reaches the polar areas cools and sinks to the surface of Earth. The sinking air raises surface air pressure. The cooled, heavier air then flows towards the low pressure zone at the equator. The speed of rotation at different latitudes on Earth and irregular topography further affect air circulation in the atmosphere. The Coriolis effect is the deflection in the pattern of airflow due to differences in rotation speed. The Coriolis effect creates a series of belts of prevailing winds and breaks up the simple flow of surface of air from the equator to the poles. The belts and cells of air are formed in the northern hemisphere and southern hemisphere at the same latitudes. The equatorial low is the low pressure zone created near the surface as heated air rises upward. The subtropical high is created by the descending air cooled at 30 degrees north, known as the Hadley cells. Westerlies are the currents that move towards the poles and away from the Hadley cells, and are diverted to the right by the Coriolis effect. The trade winds and the currents that move towards the equator and away from the Hadley cells and are deflected to the right by the Coriolis effect. The subpolar low is the zone of low pressure where the westerlies converge with cold air moving down from the poles. The westerlies and polar air do not readily mix and thus close the loop to form Ferrel cells. As the northward moving air reaches the pole, it slowly sinks and flows back towards the lower latitudes to form the polar cells. The polar easterlies are formed as an air moves away from the poles, and this air is deflected to the right by the Coriolis effect. The following sources were consulted in developing this video lecture, including content, quotations, and images.